Hello, welcome to Axial Loading. In this video I'm going to go over how to approach indeterminate axial problems, or at least a method of approaching them. Okay, so let's go here. Now, unlike a normal determinate problem, the thing about an indeterminate problem is, let's say you have your shaft and both sides on it are clamped. This means that when you set up your summation of forces in that, you're going to end up with the forces of those clamps in there, and you don't have enough equations to solve for what those forces are, making it indeterminate. So that's where the extra steps come in that you have to work with. So what we have here is a 4-step process of working through this to eventually find what all of these, what both of the clamp forces are. Now, in the process that we're working with here, in this example, it has both ends clamped. It's possible to see where you have a shaft that will elongate so far and then hit another clamp or a wall or something, and then it becomes clamped on both ends. But this is dealing with it having clamps on both ends right away. So the first step is to remove the right clamp and then solve for the net elongation just as you normally would in a normal determinate problem that we've done in the past, where the left end is clamped and the right end is free. That is step one. Solve for that elongation that you normally would, the total elongation. So here you can see we have our shaft, and you have your loads on the shaft broken up into segments like you normally would. Left end is clamped. The right end is free because we removed the clamp for now. And you can see through the summation of forces here, you can see that there's a load here on the left in that. So you can solve for the elongation after looking at all of these steps. Okay. So once you have done that, then it's time to look at the shaft with all of the loads removed, and you put a unit load on the right end where the right clamp would be. A unit load is effectively a value of 1, making it a unit load. And then you can resolve the problem for the elongation, and that gives you delta 2. So you have your original net elongation with all of the loads with the right clamp removed, and then you do it a second time with all of the loads removed, and instead of the right clamp you have 1 unit force. So here you can see it on here. All of the loads are gone, still clamped on the left, and you have your 1 unit load applied at the right end. And you can use that to solve for your second elongation as a determinate problem. Now once you have both of those elongations, then you can use this equation here, where this finds the force of the right clamp. So FR equals negative delta 1 over delta 2, where the first one is the elongation with the right clamp removed, and the second one is from having all of the loads removed and using the unit force. Now, if your FR comes out as positive, so greater than 0, that means the right clamp is pulling the shaft in tension. If your FR comes out as a negative number, that means it's in compression, pushing into the shaft. So once you've done all this, you now have the force of the right clamp. Now you can look back at your shaft, you know the force on the right end, and you can now solve for what the force is in the left clamp. And as such, you will have all of the forces found in the problem. Now, remember, in reality, both of the ends are clamped. That means this shaft can't actually elongate because it's clamped on both ends. So that's the end result that you're trying to find, is what is the forces associated with these clamped ends. And now that you've gone through this process, you've found the right clamp force, and you can finally, using the summation of forces, find the force associated with the left clamp. And that's effectively all there is to the problem. This seems kind of confusing, but as long as you approach it in the step-by-step process, it will work out. You just have to keep in mind that when you're working with an indeterminate problem, the goal is different, where you're not necessarily looking for what the elongation is, because when it's clamped at both ends, you can't. There is no elongation then. Or if you have an example where it can only elongate, say, 1 millimeter before it hits a clamp or a wall, then you already know the amount of elongation there, and then it comes down to finding what the forces are in the clamps. So that's the process that we're going to work with for solving indeterminate problems. Hopefully it becomes a little bit more clear when you see the example problem.